Hello everyone, and welcome back to our discussion of single variable calculus and our exploration of power series. Today we're going to be continuing the discussion and describing and summarizing several different properties associated to power series, Taylor series, and Maclaurin series that you definitely should know, and discuss a couple other properties that I think are important or potentially insightful in terms of how power series can be used in the realm of mathematics, physics, engineering, and other fields. So firstly, what is a power series? Well, it's just a representation of a function in terms of in some sense, infinite degree polynomial. In this case, a to the k is just a series of constants depending on what f is. And then we have x minus c to the power of k, where c is known as the center of the series. The closer the series is built around c, the more accurate the series is if you do not consider the infinite part, but rather the finite approximation. If you choose a particular structure for those constants ak, in particular if f is infinitely many times differentiable, and you represent those coefficients as the kth derivative centered at c divided by k factorial, we call that a Taylor series. And if you choose a center or convergence for a Taylor series to be 0, we call that a Maclaurin series. Now there are several functions that have nice and beautiful Taylor series, so I just want to mention a couple ones that I think everyone should know. I'm not saying these are the only important ones, but they definitely give you a lot of machinery in terms of solving problems. The very first one is the sum from k is equal to 0 to infinity of x to the power of k. This is going to be equal to 1 over 1 minus x, provided that x is in between minus 1 and 1, exclusive of 0. In this series, do you know the name of it? This is called the geometric series. Right, very, very important. Several applications there. Another series that you definitely should know is the sum from k is equal to 1 to infinity of 1 over k to the power of x. This is equal to zeta of x. There are sometimes some special values for this, but this converges provided x is in between 1 to infinity, non-exclusive of 1. And this is called a zeta. Some people will also call it a p series, or some people will also call it the zeta function, since that's the values that converges to, provided it does converge. And the zeta function obviously is a special function in term that's defined or commonly defined in terms of a power series. And then there's a particular Maclaurin series that you definitely should know for functions that we often encounter in the realm of calculus. Probably one of the most famous ones is the sum from k is equal to 0 to infinity of x to the power of k divided by k factorial. This is equal to e to the x. Your periodic functions such as sine and cosine have nice Taylor series as well. So the sum from k is equal to 0 to infinity, but they're alternating. Negative 1 times x to the 2k plus 1 over 2k factorial. So who is this? Is that sine or is that cosine? And then we also have the sum from k is equal to 0 to infinity of minus 1 to the power of k. X to the 2k plus 1 all over 2k plus 1 factorial. So is that sine or cosine? So keep in mind sine is an odd function and cosine is an even function. So even powers would be associated to the cosine of x, and odd powers would be associated to the sine of x. And you also have the hyperbolic sine and hyperbolic cosine, which is pretty much the same thing as sine and cosine, except you remove the alternating terms, right? So these are just some particular Maclaurin series, which are just Taylor series centered around 0. Right? So those are just some series that you definitely should know. Now let's do just a quick review on how to test for the convergence of series if they're not necessarily special, as I've mentioned them here. So now let's go through the most common tests that people use for series convergence. And in another video, I'll go into each of these in detail and also give examples, but here I just want to sort of summarize them here for you. So the first, let's call it, is the absolute convergence test. So do you remember what the absolute convergence test says? It says the following. If the sum of the absolute value of the coefficients converges, then the series S, the sum of the original coefficients without the absolute value, also converges. Some people we will also say S converges absolutely. The second test that you should know, and this is actually very easy to use, is called the alternating series test. And what does the alternating series test says? It says if S, which is defined as the sum of an alternating term, -1 to the k or -1 to the k plus 1, of ak is established, and ak is greater than 0 and also decreasing eventually, then the alternating series S will converge. Now keep in mind, just because AK is decreasing does not necessarily imply that it is convergent. But if AK is positive and decreasing, then this alternating series will definitely converge. Now, if you're a big fan of antiderivatives and derivatives and integrals, then the integral test will probably be one of your more famous tests to use. So if S, which let's define as the sum from k is equal to a to b of ak and I, is equal to the integral from a to b of a of x dx, then S converges if and only if I converges. So if you're very good with improper integrals, then this particular test is very, very useful. Also, if you don't know if an integral converges and you know the corresponding series converges, then that's actually very useful as well. But usually we use integrals to test the convergence of series, but you could, in theory, go the other way around if you wish. So the next is called the series comparison test. So the series comparison test. And this could be framed from 4 directions, but I'm only going to present it with 2 because you can easily get the other 2 from these 2. And the first variation says the following. So if the sum of AK is less than the sum of BK, and let's assume that the lower series diverges, so we have infinity less than something, then that something also has to be infinite as well. So if the lower bound diverges, then the upper bound will also diverge. The second kind of flips that around. So if the sum of AK is less than the sum of BK, with the sum of BK convergent, so something less than a finite number, then by comparison, the lower bound must also be convergent as well. All right, so that's what we call the series comparison test. So we compare the convergence of 2 different series. The next one, also a comparison test, but this is called the limit comparison test. All right, so the limit comparison test. So do you remember what the limit comparison test says? It says the following. So if we define L to be equal to the limit as k goes to infinity of AK and BK, so we're comparing the limit of 2 different series with L, the limit of this ratio between 0 to infinity, not inclusive of 0, then the sum of AK converges if and only if the sum of BK converges. So that means if AK diverges, then BK will also diverge, provided that this limit is equal to like 5 or square root of pi over 2 or something like that. Right? But keep in mind it requires the limit of 2 different sequences. So that means that usually comes down to you, just like the series comparison test, you have to find what series to sort of compare it to. Then we have the ratio test. The ratio test probably is one of my favorites because you don't have to sort of think of other tests, but it does have its downsides. So we define a limit, another limit L, and this limit L is defined to be equal to the limit as k goes to infinity of AK plus 1 divided by AK, the absolute value. And we're going to have 2 cases here. A, if L is less than 1, and case 2, if L is greater than 1. So if L is less than 1, then the sum of AK converges. More so, it converges absolutely. And if that limit is greater than 1, then this series, the sum of AK diverges. And if the limit L is equal to 1, then it's going to be inconclusive, so you won't be able to say anything about it then. So that's actually very, very nice, one of my favorites. Another one that we could use is, let's think about this. I think I misnumbered these, didn't I? Oh, I repeated 5 twice. That's okay. Let's just renumber them. So 5, 6, so that means this would be number 7. Number 7. All right, so number 7, so what's this? Let's do the root test. Root tests. Sometimes not my favorite, but sometimes it can be useful if you have a lot of exponentials going on. And it goes as follows. It's similar to the root test, actually, the ratio test. So if L is defined to be equal to the limit as k goes to infinity, and the reason why this is nice because it also doesn't need another series to compare to, so it's the kth root of the absolute value of that series, and we have two cases again. And it's actually pretty much the same thing as the ratio test, just root form. If L is less than 1 and L is greater than 1. So if L is less than 1, then the sum of AK converges absolutely. And if L is greater than 1, then the series diverges. Right. So those are the most common 7 tests that you can use for convergence. With the ratio test, the root test being tests that you do not need to compare to other tests aside from itself. The integral test also doesn't really need for you to look for other series to compare to. The series comparison and the limit comparison test do require a bit of cleverness to figure out which series to compare to, which sometimes isn't always that obvious. And the alternating series test and the absolute convergence test are kind of the more easier ones to consider. All right, so those are some of the tests that you definitely should know. Now let's get into some more newer or different ideas associated with power series that we haven't discussed as of yet. So let's consider this particular infinite series, which as you already know is the geometric series. What I want to do is I want to actually perform some more calculus on this expression. In particular, I want to integrate both sides of this expression. So it's likely, why would you want to do such things like that? Well, you'll see in just a moment. So what we're going to have is we're going to have the antiderivative of 1 over 1 minus x dx, and let's include our arbitrary constant c here. And then we're going to have the integral of our infinite series, the sum from k is equal to 0 to infinity, of x to the power of k dx. Now we're not going to get into the real analysis side of things where, when can you integrate an infinite series, or when can you infinite series an integral, or when can you exchange like limits of derivatives and integrals in series. We'll get into that later, so let's just assume that you can do this for now. So the antiderivative on the left is obviously going to be a natural log, and keep in mind the leading coefficient is -1 here, so we have to chain rule that out. So on the left-hand side, we're going to have -1 times the natural log of 1 minus x, and that's going to be equal to c plus. Now what I want to do is I want to integrate each of those terms of that infinite series before I take the infinite series of that. So that's going to look like the sum from k is equal to 0 to infinity of x to the k plus 1 all divided by k plus 1. So I'm just using the power rule here. Let's actually look at that infinite series to sort of see what it looks like. So we're going to have c plus. So we're going to start at 0. So 0 to anything is just itself. And then we're going to go to k is equal to 1. So we're going to have go 1 to the power of, or x to the power of 1, all divided by 1. And then x to the power of 2 divided by 2. Without the factorial, don't be tempted. X to the power of 3 over 3 without the factorial. Go away factorial. X to the power of 4 over 4, and so on. So we actually can re-index that sum instead of starting at 0 and having the k plus 1 term. We actually can write it a little bit more nicer. So we're going to have -1 to the natural log of 1 minus x is equal to some constant c, plus the sum from k is equal to 1 to infinity of x to the power of k divided by k. So we have this particular expression. Let's just multiply. Actually, let's figure out what this c is. This c is actually very, very awkward. Let's get rid of that. So what do we actually know about this particular expression? So we know that if x is equal to 0, the sum from x to the k from 0 to infinity should be equal to 0 as well. So we should get this to be equal to 0. Or we can just let x be equal to 0 and see what c would be to make that true. So once we do that, we're going to have -1 times the natural log of 1 minus 0 is equal to c plus the sum of 0 to the power of k over k. So the right-hand side series is just going to be equal to 0. Natural log of 1 is going to be equal to 0. So we have c is going to be equal to 0 to make sense. So let's assume that 0, x equals 0, is kind of the center of this geometric series. And in some sense it is, since it converges on -1 to 1, and 0 is kind of in the middle. So what we have here is -1 times the natural log of 1 minus x equals that infinite series without the c. And we can multiply both sides by -1, and we can write this as natural log of 1 minus x will be equal to minus 1 times the sum from k is equal to 1 to infinity of x to the power of k divided by k. So we have this beautiful, what it looks like is Taylor series for the natural log of 1 minus x. And we can replace x with minus x to get the natural log of 1 minus x to a natural log of 1 plus x. And write this as the natural log of 1 plus x is equal to, and then we're going to have an alternating series term, because minus 1 to the k is going to be minus 1 to the k, and we have another minus 1 in front, so that's going to be minus 1 to the k plus 1. So we can write this as the sum from k is equal to 1 to infinity of minus 1 to the k plus 1 times x to the power of k divided by k. So we have this very beautiful looking power series for the natural log of 1 plus x. Now, a very important question: for what values of x do these work? Because keep in mind, the original series that we built these from, the geometric series, only converges for x between minus 1 to positive 1, not inclusive. But it's very important to observe, at the very least, that both are centered around c is equal to 0. And the only reason that I can say this with confidence is because we can actually re-represent this particular series, and similar for the one above it, as the sum from k is equal to 1 to infinity of minus 1 to the power of k plus 1 divided by k. So that's our coefficient ak for general power series, where a of 0 is equal to 0, times x minus 0 to the power of k. Right? So that's our representation for a Taylor series, or a power series, generally speaking, right? So that means f of x, we can write it like this: so the natural log of 1 plus x is equal to the sum from k is equal to 0 to infinity of ak times x minus c to the power of k, right? So we have found a representation in this form where ak is equal to minus 1 to the k plus 1 all over k, and c is equal to 0. So this is the power representation centered around 0, but we're trying to figure out for what values of x does this actually converge. So let's see if we can figure that out. So let's just take a moment and analyze the natural log of 1 plus x, and similar analysis can be made on the natural log of 1 minus x version of it as well. So let's assume that f of x equals the natural log of 1 plus x. Let's just think of this from the pre-calculus perspective. So what does this look like? So it's obviously going to have a vertical asymptote at x is equal to minus 1, because natural log of 0 is going to be equal to minus infinity, at least in the limit. And then the natural log of 1 plus 0 will be the natural log of 1, which is 0. So it's going to be passing through the origin. So what we have here for the domain, so the domain of f will be equal to minus 1 to infinity. So these power series cannot converge for less than -1 or at -1, because the function doesn't even exist there. And the range of this function, at least from the graph and also from the domain of the exponential, is going to be the set of real numbers. And what we have here is the Taylor series function representation to be equal to the sum from k is equal to 1 to infinity of minus 1 to the k plus 1 divided by k times x to the power of k. So if we reframe our original question in terms of f and tf, then our question to answer is for which values of x does tf of x equal f of x. So the Taylor representation and the actual representation of the function, when do they match? And fun fact, it's sometimes possible that they never match at all. So it's possible that a function has a Taylor series that doesn't converge for any x at all, excluding hopefully that center point, but sometimes that center point doesn't even make sense as well. And in that case, if the center point doesn't even match, then what's the point? So definition. So suppose TF is centered around C, and let R be a positive number. Then if TF of x equals f of x for all x in the interval c minus r, c plus r, then r is called the radius of convergence. The radius of convergence of the Taylor series representation for f, and IC, not IC, but I subscript c. So IC, which is defined to be equal to the interval c minus r to c plus r, what we call the interval of convergence. Interval of convergence. Now, sometimes this could be parentheses or bracket, and sometimes this could also be parentheses or bracket. We have to do individual tests whether to know whether the left and or right are inclusive or exclusive. Right? Let's actually make a note of that. So note, usually TF at x plus or minus c, or c plus or minus r, c plus or minus r, needs to be tested separately. To be tested separately. Right? So these are the boundary points. Right? So what would we like for the radius of convergence? So ideally, take a guess. Would you want r to be large or r to be small? Ideally, we want r to be equal to positive infinity, so that tf of x equals f of x has to be true for all x in the set of real numbers, because regardless of your center, if the radius of convergence is infinity, then it covers the entire realm of the set of reals. So now the important question comes, how to find the radius of convergence. The formula for this actually looks very, very similar to a series test that we discussed already. So let's take a look at that. So the formula to find the radius of convergence r is actually found similar to how we found the limit L for the ratio test. I've just defined it slightly different so you can avoid getting confused in your formulations and your note cards and cheat sheets and all of that. But r is taken to be the limit of the absolute value of the quotient of ak divided by ak plus 1, where ak are the coefficients associated to your power series. Right, so r is equal to this beautiful and very simplistic representation. So let's take a look at our example. So we have the natural log of 1 plus x is equal to the sum from k is equal to 1 to infinity of negative 1 to the power of k plus 1 divided by k times x minus 0 to the power of k. So these coefficients right here, those are our coefficients that we're going to be using to assess or find the radius of convergence. So what would r be? So r will be equal to the limit as k goes to infinity of ak, which is going to be negative 1 to the k plus 1 all over k, divided by ak plus 1, which is the same as multiplying by the reciprocal of that. So ak plus 1 will be equal to negative 1 to the k plus 2, divided by k plus 1. And now we just need to evaluate this using whatever rules we have. L'Hopital's rule, of course, applies here, so feel free to use that if you wish. Keep in mind the absolute value will delete our negative 1 terms. So what we're going to be left with is the limit as k goes to infinity of k plus 1 divided by k. We have a ratio of polynomials, both of degree 1, so we can actually just divide their leading coefficients, 1 and 1, and we're just going to be getting 1. So this is going to be our radius of convergence for our power series. And also remember that our center for our power series was equal to 0. So now we can state, at least in its not complete form, that the interval of convergence will be equal to 0 minus 1 and 0 plus 1, which is going to be equal to minus 1 and 1. The only thing we need to figure out is, are those boundaries inclusive or exclusive? So firstly, negative 1 does not belong to the domain of the natural log of 1 plus x because it has a vertical asymptote. So this means that negative 1 is not going to belong to your interval of convergence. That means this needs to be a parenthesis. So what about 1? So if we look at 1 does belong to the domain of the natural log of 1 plus 1, or the natural log of 1 plus x, because that just turns into the natural log of 2, right? So 1 turns into the natural log of 2. So does that mean that 1 belongs to the interval of convergence? Not necessarily. So question, does the Taylor series of f at 1 equal the natural log of 2? Let's take a look. So if we look at the Taylor series of f at 1, we're going to have the sum from k is equal to 1 to infinity, negative 1 to the k plus 1 divided by k, and then we're going to have 1 to the power of k, which is going to be equal to the sum from k is equal to 1 to infinity of minus 1 to the k plus 1 divided by k. So does this converge or diverge? So obviously this is going to converge by the alternating series test. Because the absolute value form, this is just going to be 1 over k. 1 over k is positive and also decreasing. So what does it converge to? So actually what you can show is that it does converge and also converges to the natural log of 2. Some people refer to this as the alternating harmonic series, and in another video I actually prove, I'm using some fancy tricks of algebra, that this actually does converge to the natural log of 2. So that means the interval of convergence for this particular series is minus 1 to 1, inclusive of 1 and non-inclusive of minus 1. So what about other points? For example, outside of this interval, can we use x is equal to 2? Well, 2 does not belong to your interval of convergence, therefore it converging at this point is highly unlikely. So if we just try it blindly, the natural log of 1 plus 2 equals the natural log of 3. So that number is perfectly fine. So you're like, okay, can we approximate the natural log of 3 using this Taylor series? So the sum from k is equal to 1 to infinity of minus 1 to the k plus 1 divided by k. And then we're going to have 3 to the power of k. And that's going to be equal to what? So that's going to be equal to actually 2 to the power of k, not 3 to the power of k. So does this converge? Well, actually 2 to the power of k over k doesn't even decrease, right? It converges as k goes to infinity. So this actually diverges, right? So you cannot use the Taylor series at 2 to approximate. So the Taylor series of f evaluated at 2 does not equal to the natural log of 3. It actually doesn't equal anything because it diverges, right? So make sure if you want to use a Taylor series to approximate a function, make sure that the point you're trying to approximate actually belongs into your interval of convergence for that particular power series. That's very, very important to keep in mind. Let's take a look at another example. Let's consider the Taylor function representation for e to the x, which keep in mind was the sum from k is equal to 0 to infinity of x to the power of k over k factorial. Find, if you may, pause the video, try it on your own, find the radius of convergence, and then find the interval of convergence. So how would you find this? So the radius of convergence, again, is the limit as k goes to infinity of ak divided by ak plus 1, which is going to be x to the k plus 1 divided by x divided by k plus 1. Also, don't forget your factorial. So notice that everything is going to be positive here, so the absolute values are not really of interest to us. So let's actually just do some algebra here. So the limit is k goes to infinity. Let's do x to the k factorial. And then for x to the k, I'm going to decompose that in x to the k times x. And then k plus 1, I'm going to do k plus 1 times k factorial. Then I'm going to cancel. So x to the k, x to the k, k factorial, k factorial. And then this is going to be equal to the limit as k goes to infinity of k plus 1 divided by x. Now notice that this is a limit in terms of k and doesn't really care about x, but keep in mind x cannot be equal to 0 here. That's the center, and our Taylor series is approximating at other things beyond our center. So how far from 0 can you go for this to converge? Well, this is going to be equal to 1 over x times the limit as k goes to infinity of k plus 1. And k plus 1 is a monotonically increasing function. It's a linear function that goes up with a slope of 1. So as k goes to infinity, that goes to infinity. So this is going to be equal to infinity over a number, which is obviously equal to infinity. So that's going to be the radius of our convergence for our series. Keep in mind, c was be equal to 0. So that means the interval of convergence will be equal to c minus infinity and c plus infinity, and 0 plus or minus infinity will be equal to minus infinity to infinity, which sometimes we just say is r. Right? So the interval of convergence is the set of real numbers. That is, it converges everywhere on R. So you can approximate e to the power of 5 by using this series without any hesitations at all. Now, I want to mention one other very interesting thing associated to the power series for e to the x, and its connection with sine and cosine. So let's assume I is defined to be equal to the square root of minus 1, which you might remember from some time ago associated to quadratic functions and their zeros. So if we define I to be equal to the square root of minus 1, then you should be able to find that I to the power of 0 is equal to 1, I to the power of 1 equals I to the power of 2 equals minus 1, I to the power of 3 equals minus I to the power of 4 is equal to 1, and you should start to see that it's going to repeat every 4 units. So if I were to ask you what is I to the power of 5, you should say that's equal to I, because that's the next one in sequence, followed by minus 1, minus I, 1, and so on. So let's actually replace x with ix in the Taylor series for I. So e to the ix will be equal to what? Now, we haven't really talked about complex variable functions and what that actually means in the analytical sense, but we'll get to that on another day. So if we just replace it algebraically, we actually will see something very, very interesting. So the sum from k is equal to 0, so ix is going to replace x, so we're going to have ix to the power of k all over k factorial, and then this is going to be equal to what? So we're going to have 1 plus ix over 1 factorial minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the power of 4 over 4 factorial plus ix5 over 5 factorial minus x to the 6 over 6 factorial minus ix7 over 7 factorial plus, minus, and so on. And I highly recommend verifying this on your own in case you are unsure that this actually is right. So what I want to do is I want to look at all the terms that do not have I in it, which is only the even terms, because all of the odd terms does have an I in it as well. So what I want to do is I just want to regroup that. So I'm going to have e to the ix is equal to, so this things without I in it, so I'm going to have 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial plus or minus and so on. And then the things with the I in it, once you factor out, x minus x factorial over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus or minus and so on. And you should recognize what these power series are and who they represent. You should recognize those even powers as cosine. So we have cosine of x. And then the odd powers, that's going to be sine. So we have e to the ix equals cosine x plus I sine x. But e to the x is exponential, and cosine and sine are periodic. But we're kind of hanging out in the complex plane. So one thing you can conjecture, at least, is e to the ix is a periodic function, like sine and cosine. And you're like, well, the graph of e to the x doesn't look periodic, so why does e to the ix graph look periodic? Obviously, this is a question. In C, maybe it does, or maybe it doesn't. But definitely in R, it's not true, right? Because exponential functions are monotonically increasing, and sine and cosine go both up and down. But this identity that connects the exponential, sine and cosine in the complex domain is sometimes referred to as the Euler-Cotes identity. And you actually can get very, very interesting and weird connections between many constants from this equation. For example, if I consider e to the I pi, what will that be from this identity? So we're going to have cosine of pi plus I times the sine of pi. And what's the cosine and the sine of pi? So keep in mind, pi is 180 degrees. That's located here, so it's going to be minus 1 and 0. So cosine is x and sine is y. So you have this particular connection, so this vanishes. So we have e to the I pi is equal to minus 1, or you could say that e to the I pi plus 1 is equal to 0. And some people refer to this as the most beautiful equation in mathematics because it has e, pi, I, 1, and 0 on the same exact equation. Now, me personally, there are several other equations that are quite beautiful. This is not the only beautiful one, but it is beautiful nonetheless because it is simplistic and it does consider 5 numbers that are actually quite common in the mathematical world. But these are just some properties and a little review of the important characteristics of power series, Taylor series, and Maclaurin series that you definitely should know when thinking about using them in your everyday life or just your mathematical life at the least. Hope you enjoyed this video, and I'll see you in the next one. Take care.